Hello. So this video we are going to start with a small correction that we need from the previous lecture, and then we'll move to our next topic, and that is plumes in a stratified environment. So this particular graph you see is from the previous lecture, and there is this slight mistake in making this curve for q of z, where the mistake happened because now we are making z as the vertical axis, whereas this would be correct if z was the horizontal axis. So this particular curve will look something like this. Okay, so what you see here in green, this is the correct version of volume flux as a function of depth. Okay, so it starts here, and what you see here in the red is the wrong one, so please ignore the red one, that is wrong, and the green one is correct. Okay, so that's a quick correction, and now we will move to the next part of plume flows, and that is the plumes in the stratified environment. So let's first try to understand what is a stratified environment, which we have already seen in the introduction, but we will quickly revise what exactly it means and how it affects the plume flows. Okay, so you can see few images here which I found from Google, and you can see the plume shape looks quite different from what we have studied so far, right? So the plumes that we have studied so far are plumes in unstratified ambient, where plume just rises up or goes down straight vertically. But here we see plumes is not really going straight up, rather it is kind of getting diverted in horizontal direction. Right, so this is happening probably because of two reasons. One is the stratified ambient, or background air velocity. Right, so if there is an air velocity in the atmosphere, then that will obviously try to drag this plume in the horizontal direction, in the transverse direction. Likewise, if there is a stratification, and what is stratification? If there is a density gradient in the atmosphere. So if here we assume that the atmosphere has different density with height, etc. So this becomes rho ambient becomes a function of z. Here as well there is a possibility that we have rho ambient as a function of z, and here rho ambient as a function of z. So in this case, rho might be changing with height, right? With either you go vertically up, or with the depth if you go vertically down. And whenever you have this density stratification, in this case particularly the lower layer density will be greater. So in this example, I'll again pull this thing down. Here rho 1 will be greater than rho 2, will be greater than rho 3, will be greater than rho 4, greater than rho 5, greater than rho 6. So density decreases as you go up, right? And that is the stratification. That is a stable medium where you have different layers of densities, with higher density at the bottom and lower density at the top. And now what happens when plume comes out from the source, from the chimney or from some elsewhere, what happens? It tries to enter in fluid, it has buoyancy, it is lighter than the ambient, it tries to go up. But when it goes up, as we have seen in previous model, that this G prime, which is equivalent of delta C and delta T, right? So both delta C or delta T actually decreases as we go up. So in that you can see here from the blue curve, right? We start here with G prime value at this location, but as we go up, the G prime value decreases, reduced gravity decreases. That means your delta T or delta C or delta rho, they are decreasing with height. So when it decreases with height, in case of stratified medium, there will be a point, okay, in vertical direction when the plume density becomes equal to the ambient density. Okay, and when it becomes equal to the ambient density, the plume will not be able to go further up, rather it will try to flow sideward, or it might in fact come down, as you can see in this case, right? So here it is coming down, here it is going horizontally sideward, and in this case as well it went up and coming down. So these are all happening either because of stratified ambient or background air velocity, right? And what exactly again happens here? So as we discussed, plume density, so let's say there was some delta rho here. So as we go up, delta rho decreases, right? And there will be a point when delta P will become equal to, sorry, not delta P, rho P will become equivalent to rho A, because rho A is also decreasing and delta rho is also decreasing, right? Whereas in case of unstratified ambient, rho A was constant, only delta rho was decreasing, right? So the rate of decrease of delta rho in this case will be much higher than that in case of unstratified ambient. Okay, and what happens here is, once it reaches a horizontal level, its temperature decreases, delta T decreases, or its delta C decreases, right? The density difference or concentration difference, and plume actually flows sideward. In the process, it also loses its energy, it loses its temperature, etc. And slowly there is a chance that plume might become heavier than the ambient, right? And that might happen because if it loses its temperature, and let's assume that plume is coming out as a both temperature difference and concentration difference. So later that concentration difference that it may have with the ambient might actually bring the plume down, right? And that is how this pollution happens. This hot fluid does not always go up, it actually tries to come down later in time, right? And this happens more during, let's say for instance, in winter season, when we have stratification of density because of fog, right? If you look at these big cities, especially in the northern India, including New Delhi or Kanpur, we have huge fog problem during winters, and that fog actually brings stratification in the ambient, and then whatever hot gases that comes out from a source actually is not able to go up because it does not have enough buoyancy. It loses its buoyancy very quickly, and it tries to mix with the ambient, or in fact it comes down, right? And that is how it pollutes the environment even more during winter, and that is something you might have been seeing in news, or you might see in weather forecast, that AQI is generally very high during the winter season, right? And this is one of the reasons. Okay, so now let's try to understand this first experimentally, and also we will try to derive a theoretical solution for this. Okay, so we will assume that the background velocity or ambient velocity is 0 for simplification at present, and we will solve only for stratified ambient. Okay, so we'll start with that, with background 0 background velocity, and that is why in such case you will see this kind of plume. Okay, so what you see here in the left is unstratified ambient medium, and the rho here, rho atmospheric or rho ambient is constant, right? Whereas in this case rho ambient is a function of z, and in it is rho ambient is decreasing as z increases. Okay, and that is why the plume that is coming into the system with some delta rho, the delta rho decreases as z increases, and there will be a point when delta rho somewhere here, delta rho will become almost equal to 0, because that is the case when rho p is almost equal to rho ambient. Okay, and when it happens, your plume, instead of going up, it actually starts going sideward. Okay, it flows sideward because it loses all its buoyancy to be able to flow upward, and it can only move sideward. Okay, whereas in case of unstratified medium, in case 1, right, rho a is constant, so whatever delta rho you inject the fluid plume with, delta rho also decreases as z increases, but delta rho tends to 0 only as z tends to infinity. So theoretically it will become 0 only at the infinity height, right? And that's why plume in unstratified medium continuously rises up, whereas in case of a stratified medium it comes to it stops after rising to a certain height. Okay, so to be able to solve this problem, we will derive a solution called Morton-Taylor-Turner model, which is popularly known as MTT model for plumes. Okay, and this model can be applied to unstratified medium as well, but we obviously use another method to find a solution in that case. So here we will use the proper Turner model to find solution for plumes in stratified medium. Okay, so MTT model actually accounts for starts with volume flux balance, and then momentum flux balance, and then buoyancy flux balance. Okay, so these are 3 different equations we will derive as and they will work as governing equation for the problem. Okay, where volume flux basically represents mass conservation, right? Momentum flux is basically momentum conservation, or you can also say force balance, right? And this one is energy conservation. This is equivalent to energy conservation, where we have seen these with C or with T, right? So here we will write buoyancy flux equation, which is obviously not directly related to C or T. Here we use the density difference, but this is equivalent of energy conservation, which we have derived previously for temperature, or solute transport equation for concentration. Okay, so let's start with mass conservation. So to be able to do that, let's consider that we have a plume which is going up, and rho ambient here is a function of z, and this is coming out with some delta rho, right? Delta rho naught you can call, which is the initial density difference. Okay, and as it rises up, this q is changing, which is a function of z. Also your delta rho is a function of z, or in other words, we can call rho p as a function of z, where rho p is the plume, and here we can call it as rho naught minus rho a, where rho naught is the rho p at z equal to 0. Okay, so both q and rho p are function of z, and then obviously there is w, which is function of r and z, which is the vertical velocity. So now we will assume there is a small element, okay, which and it is circular, so if you look from the top it will look something like this. All right, and we assume that this location is z, this is z plus dz, so basically this length is dz. Okay, and here this is w, here also we have some other value of w, and we also have radius, which is basically should be distance from the center line. Okay, that is the radius of the plume. Okay, so now if we want to write a balance equation for this particular element, mass balance, how would you do that? So mass balance for the small red element, I name it as red because I have written that or marked that in red color. Okay, so there what is the volume, or here we are using volume flux balance, that is more precise. So what is the volume that is going through the lower part or crossing the lower part of the element versus crossing the upper part of the element? So that should be w bar, we'll assume that is the average velocity, w bar into pi r square times rho minus, okay, and this value is supposed to be calculated at z plus dz minus rho w bar pi r square, which is calculated at z. Okay, and all right, and we are doing the volume balance, not mass balance, and that is why we don't really need the density term here, so I'll simply get rid of it, and whether we consider density or not, it will eventually cancel with the right hand side term, so it does not really make much difference. Okay, and now in this Plume model, one thing which we know is so because of entrainment, there is continuous fluid that is coming from outside to inside. Okay, and that rate with which the fluid coming in is, let's say that is u, that is the horizontal velocity, right? So u of z is the horizontal entrainment velocity. Okay, so while plume is going up, there is also entrainment happening, and in this horizontal velocity is generally given as a function of w, so this is proportional to the vertical velocity. Okay, and experimentally this is found that this is equal to this particular expression where a here has a value of 0.13. okay, and that 0.13, or to be precise is 0.25, and this A is known as the entrainment coefficient, and this value is found experimentally. Okay, so this is how your horizontal velocity, entrainment velocity, is defined for a plume, and this is considered as proportional, linearly proportional to the vertical velocity. Okay, and the ratio between entrainment velocity versus vertical velocity is equal to 0.125. Okay, so now coming back to the volume flux balance in this case. So there is obviously a change of volume if you go from the lower part of the element, this red element, to the upper part, because upper part has got broadened. That means more volume is going through that part. So that change in volume must be equal to the volume of ambient fluid that has come into the plume, right? And that must be equal to 2 pi r, that is the circumference, dz, that is the area, right, and multiplied with u. Okay, so that is the horizontal velocity with which the ambient fluid is coming into the plume, and that is the rate of change of the plume flux, volume flux, right? So what you get here is, we will simplify this further. So this is calculated at dz minus w pi r square, this is calculated at r, and this becomes, where u is aw, so we will call it dz. Okay, so this is clear. This left hand side flux is the vertical flux and right hand side flux is the horizontal flux, and they must balance the total flux within that red element. Okay, so this gives us the volume flux balance. And now if we consider the vertical length scale to be extremely small, if dz tends to 0, if that is very small, then we can actually approximate this equation to be simply d by dz pi r square 2 pi a w bar r. Okay, and here pi will cancel out, so this equation becomes d by dz r square w bar is equal to 2a w bar r. Okay, so this is, we will call it equation A. So this is the volume flux balance, and now we will also find out the momentum flux balance and buoyancy flux balance.